Team 2 will be presenting about tokamak toroidal field co-optimization. The system includes three subsystems, namely support structure subsystem, cooling subsystem, and blanket wall subsystem. The input, output, and linking variables of the system is as followed. This is the system flow diagram. The system boundary includes the three subsystems. The subsystems are governed by rigid physical interdependencies, where the cooling system's thermal discharge serves as the blanket heat sink, while the geometric dimensions of both the cooling channels and blanket thickness dynamically scale the total structural load applied to the support structure. A system-level approach allows the optimizer to negotiate global trade-offs, such as the pumping power penalty versus the structure savings from reduced blanket mass that would otherwise be ignored by isolated subsystem models using static parameters. The parameters are as followed. The shared and local design variables were as followed. All the design variables were real values. The intermediate and coupling variables were as followed. There were mainly two coupling variables. One was thermal coupling, indicating that the blanket wall inlet temperature is identical to the outlet temperature of the cooling subsystem. The other was the structural load, which was governed by the dimensions of the cooling and blanket wall subsystems. The constraints were as followed. They included coolant boiling limit, pump pressure limit, blanket mass limit, blanket thermal limit, minimum shielding thickness, structure stress limit, structure buckling limit, and mass flow consistency. The optimization function was the total cost composed with cost of each subsystem. The cooling subsystem cost was mainly dependent on the mass flow rate and channel dimensions, while the blanket wall subsystem and support structure subsystem costs were mainly dependent on material use. Objective constraint trade-offs were as followed. In the cooling subsystem, the optimizer navigated the cubic relationship between mass flow rate and pumping power, balancing the need for low temperatures against the escalating operational costs. The blanket subsystem faced trade-off where increasing thickness improves thermal shielding and safety, but incurs significant material cost and adds parasitic weight to the weight system. The structure subsystem minimized its own material volume while ensuring the truss remains robust enough to withstand the loads imposed by the thermal components without buckling or exceeding stress limits. Difference from subsystem models was that unlike the interim models that treated interdependent variables as static, this system-level approach dynamically updates linking variables such as the core rate and blanket inlet temperature. Overall, the individual discipline feasible architecture was adopted.
Our system uses three modeling approaches. The cooling and blanket wall subsystems are modeled analytically. The cooling uses an energy balance for joule heating and a Darcy-Weisbach correlation for pressure drop, while the blanket uses a steady-state energy balance for outlet temperature. The structural subsystem uses a finite element simulation of a 2D truss with an assembled stiffness matrix. A few important assumptions to note. We assume steady-state conditions, constant material properties, and pin-jointed members under static loading. The cooling loop uses liquid nitrogen and the blanket uses water, so they operate independently. The only thing connecting all three subsystems is the coil weight, which depends linearly on the hydraulic diameter and blanket thickness. This diagram shows our 5-step computational pipeline. In step 1, the cooling model computes joule heating, outlet temperature, and pressure drop from mass flow rate and hydraulic diameter. In step 2, the blanket model independently calculates modular mass and outlet temperature using its own water coolant loop at 343 Kelvin inlet. Step 3 is the key coupling. The total coil weight is updated as a linear function of dH from cooling and T from the blanket. This weight feeds into step 4, where the structure model generates the truss geometry, distributes the coil weight across boundary nodes by arc length ratio, then assembles the stiffness matrix and solves for stresses and buckling loads. Finally, step 5 sums all three subsystem costs into the total objective. The blanket material cost dominates at 7.84 million, while cooling and structural costs are essentially negligible. For the optimization, we use MATLAB's FMINCOM with sequential quadratic programming under an individual discipline feasible formulation, where the optimizer handles all 9 variables simultaneously. We choose SQP because all variables are now continuous. In the interim, the structure used a genetic algorithm where n was an integer, but fixing n at 5 eliminates that. We ran 5 different initial points with up to 5,000 function evaluations, each to guard against local minima from the nonlinear subsystem coupling. Here are the results from all 5 runs. Every run converged to the same optimal cost of $7.84 million, with 7 of the 9 variables identical across all the runs. The only variation is in pipe diameter d and velocity v, which I'll discuss on the next slide. The only active physics constraint is the pressure drop limit, and 3 side constraints hit their lower bounds: mass flow rate, thickness, and theta scale. All 5 runs reported successful convergence. Here are 4 key takeaways from the results. First, all 5 runs from different starting points converged to the exact same optimum of $7.84 million, with 7 of the 9 variables identical. This gives us strong confidence it's the global minimum. Second, the blanket pipe diameter d and velocity v are the only variables that differ across runs, but they don't affect the cost at all since they don't appear in the objective function. Third, the blanket cost completely dominates at $7.84 million. That's 99.9% of the total. The cooling and structural costs are negligible by comparison, which is why the optimizer pushes thickness to its lower bound. And finally, only the pressure drop constraint is active along with 3 side constraints at their bounds: mass flow rate, thickness, and theta scale. This suggests that relaxing these bounds could further reduce cost, which motivates the sensitivity analysis.
We will present the post-optimality sensitivity analysis for our project. Our objective is to quantify how small perturbations in constraints and model parameters impact the final optimal objective value. For the constraint sensitivity analysis, we focused on the active inequality constraints about pump pressure and 3 design variables that reached their lower bounds at the optimum: mass flow, blanket thickness, and angular span scale. For the parameter sensitivity analysis, we applied a 10% perturbation to evaluate 3 specific parameters: blanket area, base coil weight, and elastic modulus. These were selected to represent the geometric scale, structural load, and material properties of our system, respectively. Constraint sensitivity analysis results indicate that the optimal objective value is extremely sensitive to the lower bounds of blanket thickness. This suggests that the current shielding thickness requirement is the primary bottleneck preventing further cost reduction. In contrast, relaxing the pump pressure or mass flow rate constraints yields negligible improvements to the total cost. The parameter sensitivity analysis results shows that blanket area is the most influential parameter. Conversely, the sensitivity to the elastic modulus is low. This implies that the optimal cost remains stable even with minor fluctuation in material properties, demonstrating the robustness of our design. In conclusion, the sensitivity analysis confirms that blanket design is the core focus for system optimization.
Our optimization results show strong and consistent convergence across all runs. Regarding of the initial starting point, every run converged to the same optimal cost of approximately $7.84 million, which was mentioned previously, but I really wanted to emphasize that. This provides strong evidence that we identified a global minimum rather than a local solution. In addition, 7 out of the 9 design variables were identical across all runs, indicating high solution stability. From a constraints perspective, the pressure drop constraint is the only active inequality constraint at the optimum. We also observed that several variables, including flow rate, blanket thickness, and angular span, are pushed to their bounds, meaning the system is operating at its physical and design limits. One of the most important insights from our results is that the blanket subsystem dominates the total system cost, contributing nearly all of the overall cost. In contrast, the cooling and structural subsystems have a negligible contribution at scale. meaning that the system level design is primarily driven by the blanket. From a physics perspective, the system is fundamentally limited by thermal constraints, specifically the boiling point of liquid nitrogen. As a result, the optimal design operates just below the boiling point to maximize heat removal efficiency. This is expected engineering behavior. This creates this key trade-off. Increasing the coolant flow rate reduces temperature, but significantly increases pumping cost due to its nonlinear and roughly cubic relationship in engineering terms. Therefore, the optimizer must carefully balance these competing effects to achieve the lowest cost. Keynote: the system level optimization shifts focus to the blanket cost, while the subsystem models focused more on cooling trade-offs. Next, our sensitivity analysis highlights what drives the system design. The most sensitive design variable is the blanket thickness, meaning that even small reductions in the minimum thickness requirement can significantly reduce total system cost. Similarly, the blanket area is the most influential parameter, reinforcing that the blanket subsystem dominates system behavior. In contrast, the system shows low sensitivity to material properties, just showing that the optimal design is robust to small changes and uncertainties regarding material properties. These results are also consistent with expected engineering behavior as the system operates within the typical liquid cooling range of 77 to 105 degrees Kelvin. Compared to the subsystem level optimization, the system level model reveals the blanket dominates total cost, again emphasizing this, whereas the cooling trade-offs were more apparent within the subsystem themselves. For future work, we can focus on improving thermal model fidelity, such as incorporating transient effects and exploring alternative cooling strategies to move forward with this project.